The first thing that we did in this unit was calculate momentum. Now, when we did that, the momentum in those questions was the same throughout the whole question. So if we had the velocity in that question, or maybe we had to find the velocity in that question, but it was the same velocity for the whole question. We were able to find momentum fairly easily by multiplying that velocity by the mass. Then we moved to questions where the velocity changed. Maybe the object was falling, so the velocity increased, or it was going up into the air, so it decreased. We wanted to find the momentum at a specific point in time. To do that, we had to find a specific velocity, not the overall constant velocity, but a specific velocity, the velocity at one moment in time, use that to plug it into our equation. Well, today, we're going to go a little bit further. Today, we're going to look at problems where the velocity is changing again. The momentum is changing again. But we're not going to quantify the momentum at a specific moment in time like we did in the last group of questions that we did, but rather, today we're going to quantify the change in the momentum, the overall change, not the momentum here or then, but the momentum change between now and then. We call this impulse. Impulse is defined as the change in the momentum, the gain or the loss in the momentum. Now we have to assign a symbol for impulse. There's an equation, as you might guess, for impulse, and that equation is just like for momentum, using words, certain value. But whenever we're writing it, we want to put a symbol to it. The symbol for impulse that we're going to use is delta P. Why? Because it's a definition. Impulse is a change in momentum. Momentum is P, impulse is delta P. It's a vector because momentum is a vector. If velocity is a vector, then the change in velocity will be a vector. If acceleration is a vector, then change in acceleration will be a vector. If force is a vector, then change in force will be a vector. If momentum is a vector, then change in momentum, impulse, will be a vector. Now, I'm going to take you back to Newton's second law, if you remember that from Physics 20. Remember Newton's first law said, object at rest stays at rest, object in motion stays in motion, straight line, constant speed, until acted upon by an unbalanced force. The third law told us the action-reaction relationship. Object A applies a force on B, B applies an equal and opposite force on A. The second law was the math one. F is equal to m times A. You guys remember that? Now, I'm going to do some substitutions here and see what comes out of this. I'm going to replace A with delta V over delta T. Is that okay? Can I do that? Is that allowed? Sure it is. Why not? Let's rearrange this a bit now. Let's take the T up by multiplying. It becomes F times T is equal to M times delta V. Is that okay? Let me ask you this question. What's M times V equal to? Well, momentum. Good. M times V is equal to momentum. All right. If M times V is momentum, then what would M times change in V, delta V, be equal to? If mv is momentum, then M delta V would be change in momentum. That was the definition for what? Impulse. So what we're saying here is that F times delta T equals M times delta V equals impulse. Now this equation is partially on your data sheet. The red part that I have circled there is on your data sheet. The rest of it isn't, but that's okay. We know that M times delta V is equal to impulse. We just have to remember to write that down if we need it. Let me ask you another question. Impulses change in momentum. There's a car traveling down the road, has a certain amount of momentum. How do we change that car's momentum? In other words, how do we get that car to speed up or to slow down? What do we got to do to it? Yeah, you got to push it or pull it. You got to apply a force on it. What's required for impulse to happen, for a change in momentum to happen? You got to apply a force. And the longer you apply that force for, the more time you apply that force for, the more the impulse is going to be, the more the change in momentum is going to be, right? You push on a car with friction, let's say. It's going to cause that car to slow down. You push on the car with friction for a longer time, it's going to cause the car to slow down even more. Two things are required to have that impulse, to have that change in momentum. It's going to be force, it's going to be time. Now, we're going to solve problems using what we just learned, but understand that what we just learned is really just another form of Newton's second law of F is equal to m times a. So whenever we have a problem that I'm telling you you probably should use impulse for, remember that F equals ma is technically still valid. It still applies. And if you're struggling too much with impulse, go back to F equals ma. Because sometimes it's a convoluted way, but eventually it'll end up working out for you. All right, when are we going to do it? Well, the most obvious one is when the question asks us for impulse. I got a 4-year-old who could probably answer that one for me, right? When do you use impulse to solve a question? Well, when it asks for it. He would have no idea what impulse is, but he would know that if it asks for something, then that's what you do. Question says, how much impulse does the car experience as it comes to a stop? Use impulse. If the question says, what's the change in momentum, or the momentum gained, or the momentum lost, or how much momentum does the object gain, or how much does it lose, then we can use impulse. That's a relatively straightforward one as well. Not quite as straightforward as the first one, but almost. And finally, the third one, this is the one that's more of a read between the lines kind of thing. If the question has a force and it has a time in it, it may not mention the word impulse anywhere in the question. In fact, it may not even mention the word momentum anywhere in the question. If you see a force and a time, maybe the word force, maybe just a value for force, anywhere in the question, then let's try impulse. Let's try one. This one's on page 458 of your textbook. It says, to improve the safety of motorists, modern cars are built so that the front end crumples upon impact. Do you guys know that? When a car crashes and it's smashed into smithereens, destroyed, that it's supposed to do that? They could build cars that are much more rigid and much stronger and survive a crash better, or appear to survive a crash better, but they don't. They don't because they, by design, want the car to suffer the damage. Something's got to suffer damage, right? It's designed so that the car suffers the damage as opposed to the person in the car that suffers the damage. We sacrifice the car via the crumple zone as opposed to sacrificing the person inside the car. So in this question, a 1,200 kilogram car traveling at a constant velocity of 8 to the east hits an immovable wall and comes to a complete stop in 0.25 seconds. So good news is this car is not going all that fast, maybe about 30 kilometers per hour. But it comes to a stop really, really quickly. We want to find the impulse provided to the car, and we want to find the average net force exerted on the car. Question C, we'll worry about that later on because we'll come back to it. But we'll worry about it after we're done the other two because we're changing something there. This is an impulse question, right? It asks us for impulse. We see a force and we see a time in it. The car is coming to a stop. Its momentum is changing. It's an impulse question. The mass of this car is 1,200 kilograms. The velocity of this car initial is 8.0 meters per second. The time interval is 0.25 seconds. Anything else we have there? Read between the lines. Anything else? Right? Yeah, good. Your final speed 0 comes to a stop, right? We want to find, what, the impulse, and we want to find the average net force. Notice it says, Mac, the average net force. Maybe it's going to be a constant force. Maybe it's going to be changing. Okay. If we calculate the average, it would be the same value if it remained constant the whole time. So if we see that word average in an equation, it's okay to use it. If we don't see the word average in the equation, as long as they mean constant, it's okay to use it. All right, let's say delta P is equal to F times delta T is equal to M times delta V. The three parts of that equation. We've got M, VI, VF. Let's use this part. Delta P is equal to M times delta V. We'll skip the F times delta T at least for now. M is 1,200 kilograms. Delta V is, be careful with this, 0 minus 8, not 8 minus 0. Final minus initial. 1,200 times negative 8 is negative 9,600. Or negative 9.6 times 10 to the 3. What's the negative mean there? You could think of it in two different ways. What's one way? Right. Okay, but why is the change in momentum negative? What does that mean? What does it mean when you have a negative change in momentum? Yep. Okay, change in direction from velocity. So in other words, if you are moving to the right, the impulse is to the left. Does that make sense? If you are moving to the right, the change in momentum is to the left, negative value. The other way to think of it is it's a loss of momentum. You had a certain value, now you have 0. It's a loss of 9,600. It's a good B now. B says that what's the average net force? Now let's say delta P is equal to F times T. Because we have delta P, and we have T. It's negative 9,600 divided by a time of 0.25 seconds. 19.2, 38.4, 3.84, negative 3.84 times 10 to the 4. Yep. Yep. It's a big force, right? That's going to hurt. If you're a passenger in there, it's a car, it's going to hurt. It's a big force. But if there was no crumple zone, it would hurt more. We'll see why in just a second. Let's take a look at C. That'll explain why. For the same impulse, what do they mean by that? For the same impulse. This car has what I call a predetermined impulse. It isn't changing. You're traveling down the road at 100 kilometers per hour. You have a certain momentum. One thing we know for certain, at some point you will have 0 momentum. We know for sure with 100% certainty what the impulse you will experience is. If your momentum is 10,000, we know that your impulse will be negative 10,000. 0 minus your value right now. What we don't know is how much that's going to hurt. The impulse is predetermined. It's determined by the initial conditions. The car is traveling down the road at a certain speed with a certain mass. The impulse is going to be the same no matter how that car comes to a stop. Okay, this impulse is the same as it was in question A and B because that car is moving at the same speed, 8 meters per second, has the same mass. The momentum of that car is 9,600. The impulse will be negative 9,600. What's different, though, is the force. Because although the impulse is the same, the time isn't. It's much quicker now. Instead of crashing in 1/4 of a second, it's crashing in 1/25 of a second. It's all happening so much quicker. We do the math here. Works out to be negative 2.4 times 10 to the 5 newtons. It's a bigger force, right? Why? The impulse was the same, but the stopping time was less. It stopped quicker. When you stop quicker, it means it hurts more. Matt, can you stand up on your desk for a sec? Just don't see your desk. Stand up on your desk. When I count to 3, Mac's going to jump off of his desk, okay? Count to 3. Mac, here's the condition. When you jump off your desk, you're going to not bend your legs. 1, 2, don't do that. Why not? Why am I not going to tell him to jump off the desk and not bend his legs? It's going to hurt his knees, right? Why is it going to hurt his knees? Jump off the desk now, however way you want. Okay, he bent his knees. Intuitively, he knows to bend his knees, right? What difference does that make? Why does bending his knees help, not hurt his knees? His knees can absorb the shock, yeah. It increases the amount of time. The impulse experienced by Mac as he hit the ground is going to be the same no matter whether he bends his knees or not. It's predetermined. But if he bends his knees, it increases the stopping time, which decreases the force. That's the whole point behind something like an airbag, right? Your head hits an airbag. It takes longer for your head to stop. Same impulse, but longer stopping time, smaller force. Okay, that's the whole point. Anybody play basketball here? Yes? Okay. Not everybody plays basketball on a team, but people play basketball, or baseball for that matter, right? When you catch a basketball, Haley, you don't brace yourself like this. Stick your arms out like this, and then just catch it like this, because it bounces off your hands, right? What do? Without even thinking about it, you cradle it, right? Your arms go back a little bit. What does that do? It increases the stopping time of the basketball, which decreases the force, which means it's going to hurt your hands less, and you're more likely to be able to hold on to the ball because it's a smaller force. Okay. All right. Going to give you a couple questions to work on with this stuff, this impulse stuff. Page 458, you can have some time to work on those questions now.